Behavior of the radial wave function near the origin. So we can start from the Schrodinger equation, and it is for hydrogen atom. It is the simplest case. And the Schrodinger equation for the radial wave function is the equation number 1, that is minus h cross square by 2 mu d square by dr square plus 2 by r d by dr plus L into L plus 1 h cross square by 2 mu r square plus V of r into r is equal to ER, where r is the radial wave function, and we are introducing a function ur through r is equal to u by r, and we can substitute this equation in equation number 1. Then this equation becomes this one, that is equation number 2. And this radial equation has the same form as the one-dimensional Schrodinger equation, and this is our one-dimensional Schrodinger equation. Both these have the same form. And here the potential energy term, instead of this potential energy term, here is, you can see this term, that is, it is the effective potential energy. Okay. So, but with the effective potential energy, V effective is equal to L into L plus 1 h cross square by 2 mu r square plus V of r. And the complete solution of Schrodinger equation has two parts, that is radial part and angular part. So, the complete solution, that wave function, wave psi is the wave function, and this can be, it is formed of radial part and angular part. This is the radial part and this is the angular part. And we have to normalize the radial and angular part separately. Okay, here our concern is radial part, that is integral 0 to infinity r square dr r square is equal to 1. That means there is a probability for finding the particle between r is equal to 0 and r is equal to infinity is 1. Okay, and this is the angular part. Anyway, from here we know that r is equal to u by r. So instead of this r, we can substitute this ur by r in this equation. Then r square and r square cancelled. Then u of r square into dr is equal to 1, or u integral 0 to infinity u star r into dr is equal to 1. Now assume that a solution near the origin is of the form of a power series ur is equal to r to the power s. Then du by dr is equal to s into r raised to s minus 1, and d square u by dr square is this one. Now we can substitute all these things in equation number 2. In equation number 2 here, instead of u, we can substitute this. Then the equation becomes this one. And here the first part is this one, and the second term is here r square. So r square and r raised to s will combine, and r to the power s minus 2. Next, for small r to the power s minus term will dominate. We know that if it is r is small, then this when we compared with the r to the power s, this r to the power s minus 2 will dominate. That means r to the power v of r tends to 0. So for small r, the coefficient of r to the power s minus 2 can be equated to 0. That is, this is the coefficient term. So minus s minus 1 plus L into L plus 1 is equal to 0. That is minus s plus L square plus L is equal to 0. That means L plus s into L minus s plus 1 is equal to 0. From this we know that either L plus s equal to 0 or L minus s plus 1 is equal to 0. So from this, L plus s equal to 0 means s equal to minus L. And if L minus s plus equal to 0 means s equal to L plus 1. Then our solution is of the form ur is equal to r to the power s. So we can substitute instead of s, that means r to the power L plus s, or r to the power L plus 1, or r to the power minus L. So here this r to the power minus L, we are discard the r to the power minus L solution for all L, because 1 by r behavior of r cannot satisfy the Schrodinger equation. We just ignore this one. Okay, we are taking this one. So the allowed behavior of small r is given by ur is equal to r to the power L plus 1. Okay. No, it is actually L plus S. L plus S. L plus 1. Sorry. Here S equal to L plus 1. So here also S equal to L plus 1. Then R is equal to R. We know that it is U of R by R. So R to the power L plus 1 by R is equal to R to the power L. And hence U of R must satisfy this condition, that is UR is equal to 0. As L increases, the particle is less and less likely to be found in the vicinity of the origin. The effective potential energy, this is the effective potential energy. Here this term is known as the centrifugal barrier, which increases with the increase in L. If L is increases, then this barrier will increase, and it tends to keep the particle away from the origin. If it is, there is a barrier, no, so it keep the particle away from the origin. Then this equation r is equal to r to the power L. The radial wave function vanishes at the origin for all except L is equal to 0 or S state. So there is a graph connecting small r and effective potential energy, and for different L values, that is L equal to 0, L is equal to 1. That graph is it is in the textbook. You just refer that. Okay.